All right, and just to start some new material here, this will not be on the midterm, but it's the next thing we're going to look at, and it's frames and machines. So what we have with frames and machines are members that are assembled together, kind of like trusses. And what machines do is move things and exert forces. What frames do is bear a load. Now, these are different than trusses in that you can't assume that each of the members are two force members. That's a key assumption in trusses, but it is not used in frames and machines. So a frame doesn't move, it supports a static load. A machine does move, it exerts a force and moves a load. All right, now if we look at some of the parts of analyzing frames and machines, what we want to look at here is we pull these things apart into exploded views. That's what we do with frames and machines. So I'm on page 560 here. Now, if we were just to take this simple little mechanism here and break it up, what we could do here would be to break it up into link AB, and then the pin, and then link BC. All right, and if we work our way through it and see what this 30 Newton load is doing, well, if it pulls to the left, pin B will pull B to the right to hold the linkage in equilibrium. So at A you got 30 to the left, and at B you got 30 to the right on the linkage. Now what's pulling on the linkage is this pin. All right, so if the pin is pulling B to the right, AB is pulling the pin to the left. So there's the 30 newtons that AB exerts on the pin. Now if that's happening, BC will pull the other direction. So that'll be 30 to the right. So we got 30 to the left on the pin from AB, 30 to the right on the pin from BC. Now if we take that to this larger plate here, whatever this is, BC, that has this cantilever attachment to the wall, what's going on there is the pin is pulling B to the left because BC is pulling the pin to the right. What that means is the pin is pulling BC to the left, okay? And then the reaction will be back to the right. Okay, so here's just a sequence of analyzing what's going on with that little system there. Working our way from member AB to the pin and then to BC. So we're just tracking the force through as it affects these different things. Now notice that you can omit the pin from the analysis. You can just start with linkage AB and then just work your way over to BC, the plate, okay? So you can just kind of skip the pin and work your way from linkage, from member to member, which is normally what we do. Now, as you do that, you want to remember to reverse the directions of forces as you go from one member to the next. So at B here, the 30 Newton is to the right. That's on AB. So on BC, the 30 newtons is to the left. Okay. All right, now another thing we get into here are pulleys sometimes, so let's have a look at that. Now these pulleys would be in static equilibrium, so they're not spinning or rotating or doing anything like that. So what we would do here is we would have a look at how these affect the members that hold them up. In this case, it would be this vertical member that's holding the pulley up. So let's see what the effects of that would be. All right. Now, what we're going to have here is this cable that wraps around the pulley. The force in it will be 200 newtons, everywhere in there because it's in static equilibrium. So we've got 200 pulling down here and down into the right on the other side. So we would end up with this diagram here of how that cable affects the pulley. Now, if we want to start working with this whole object, we're going to need moment arms here quite often to calculate moments. We're going to have to look at these little offsets over here. This one over here to the left to get to where this cable force attaches to the pulley. And then we've got one up here as well, up and to the right. Okay, so those little dimensions are going to get a little complicated. So we can use a little technique here to simplify this quite a bit. We can look at a free body diagram of the pulley. And if we look at the forces on the pulley, those cable forces, there's going to be forces of the pin back on the pulley equal and opposite. So we're going to have forces like that on the pulley exerted by the pin to counteract these two forces here, okay? And just as we were doing before, we can look at now at what the pin does to this standard here, this vertical member. If the member here is pushing up on the pin, well, if the member is pushing up on the pin with 200 and 200 directly up and then up and left with the 200 here, what the pin does is the opposite. It's going to push down on that member and down right on the other side there, okay? So the gist of this is you can take these cable forces and move them to the pin. If you got to move them both at once, so you can pick both of those cables up and just attach them right to the member and analyze the member in that fashion, and that'll work out just fine. So that's a simplified way to analyze this member, where you can avoid having to calculate all these little offset distances here, okay? So that's normally how we do it. We just take the cable forces and move them both to the pin on the member. Okay, the last little thing here I want to go over is on 561, and that relates to the fact that we can't assume that these members are two force members. That's not how we approach these problems here. So what that means, so if these were two force members, now they're not, but if they were, if that were a truss, what you could do is just look at this reaction here at A, that's a roller, so that would be a vertical reaction, and then use this equation here to analyze the force in ACG. And it would be pretty straightforward. But when you're doing a frame, as we're seeing here, you can't assume that ACG is a two-force member, and it's not. I mean, you've got three forces in there at A, at C, and at G. So I can't assume that I've got an axial load doing this. I just can't assume that that load comes in at 30 degrees down left anymore, because ACG is not a two-force member, okay? So this complicates the analysis a good bit. So for these frames and the machines too, you can't make that assumption that I've got there, okay? It just doesn't work. So you have to go through a little bit more of a complex analysis to get these forces figured out. So you can't assume that, nor could you make a similar assumption at D, okay? Now, it is important to identify two force members in frames and machines, because that can greatly simplify your analysis. So if you look at this one here, this triangular frame, there is one two-force member in there. And if you have a look at it, maybe just think about it for a minute and identify it, because you do want to be able to identify these, okay? And it's CB. See, two pins, no force in between. That's a two-force member. ABD has three pins, so it's not a two-force member. ACG has three pins, so it's not a two-force member. GD is actually GED because there's a force applied in the middle. That has three forces applied to it, so that is not a two-force member. So the only one is BC. Now in this bucket here, the two force members that we want to be able to identify, and we want to start being able to do this just by looking at them, are those hydraulic rams there that are attached. They have two pins on them, and so they either push or pull at compression or tension. So those, I guess, hydraulic cylinders would be a better word for that. Those are two force members, okay? So we'll start in next time in analyzing some of these frames and machines. The general approach is to create an exploded view of the frame and machine and use equilibrium analysis to work your way through the problem.